Hey there, Mr. Sutton here with the AB Calculus 4.4 lesson on concavity. In this one, we are using the second derivative test to see where a function is concave up or concave down. For a warm-up on this one, just a little thought question here. We ask ourselves, if f prime tells us the slope of f, in other words, whether f is increasing or decreasing, what does f double prime tell us? About f prime or about f? So if we think about this, f double prime is the derivative of f prime. So it's telling us how f prime, the slope, is changing, whether f prime itself is increasing or decreasing. In terms of what this tells us about f, it gives us a concept that we now call concavity. So there's two different types of concavity, and to illustrate them both, let me show you this graph here. It has both of them. So if f double prime is positive, that means that f prime itself is going to be increasing. And if f prime is increasing, what does that do to the graph? Well, it depends on whether f prime, the slope itself, is already positive or negative. If you have a slope that's already positive, like right here, and you're making it more and more positive, then you're essentially speeding up in the positive direction. But hold on a sec. What if your slope f prime is negative? What if you're going down? If you're increasing a negative number, you're making it less negative. You're making it closer to the positive end. So you would be slowing down your negativity like on this part of the graph. Now, if you put all this together, it gives the original graph, f, something called a concave up feature. So this spot from like here over to here, we would classify this as concave up. Sometimes we're going down, sometimes we're going up, but along the whole interval here, f prime is increasing the whole way, from negative to positive. Now, what if f double prime itself is negative? Well, in that case, f prime is decreasing. And if f prime is already positive, like in this part right here, if the slope is already positive, decreasing makes it less positive, so we're slowing down. But if the slope's negative, decreasing makes it more negative, so we'd be speeding up in that direction. This whole effect here on the graph of f is called concave down. And if you have trouble remembering which is which, well, up like a cup and down like a frown. Now that we've got the gist of what concavity looks like visually, let's talk about it algebraically. Let's say we want to find the intervals where a graph is concave up and concave down, and we don't have a picture to look at. How could we do this? Well, since we saw that concavity is essentially whether or not your second derivative is positive or negative, we just need to do sign analysis on the second derivative. So pause the video, find that second derivative, do your sign analysis, and draw some conclusions. Give it a shot. All right, so our first derivative on this, that's going to be 3x squared minus 12. And we need one more derivative now, because this first derivative just tells us increasing versus decreasing. So for the second derivative, we've got 6x, and then that 12 is getting zeroed out. Now for critical values, we just want to know where this equals 0. So that's going to happen when x equals 0. And for our sign graph now, notice I'm putting f double prime on here. So this is going to be a critical value at 0. If I test something a little bit to the left, like -1, note that I am now plugging this into f double prime, not f prime. So plugging it into f double prime, that's going to be a negative. And if I plug a positive like 1 into f double prime, that's going to come out positive. So based off of this, we can conclude that our graph is concave up wherever second derivative is positive, so from 0 to infinity. And we can conclude our f is concave down on negative infinity to 0, because that's where f double prime is negative. Now, in terms of abbreviations, there's no universally accepted abbreviation for concave up or concave down, like there is, pos neg and inc dec for all those other concepts. So you should write it out each time if you want people to know what you're talking about. Here's another concavity example for you to try out. This one is also going to be without a calculator. Pause the video and give it a whirl. All right, so our first derivative on this, that's just going to be cosine of x. Second derivative is negative sine of x. So far, life is good here. And we need critical values for that. So where does that equal 0? Well, this is going to equal 0 wherever positive sine of x equals 0. That's going to be where your y values are 0 on the unit circle. So that would be at 0 radians, pi radians, pi over 2 radians, and we could just keep going around. but they gave us this interval here so that we don't have to do that. All right, so these are our critical values. Let me make an f double prime line here. And I have endpoints on this one because they gave me endpoints at 0 and 2 pi. They also happen to be two of our critical values. So the only one on the actual interval is this pi here. So something to the left of pi I can test out. Well, how about pi over 2? Now I'm plugging this into negative sine of x. Normally this sine of pi over 2 would be 1, so this is really negative 1, which is a negative. And something between pi and 2 pi, let me try 3 pi over 2. That would normally be negative if you plugged it into sine, but now this negative out front makes it positive. So for this one, we are concave up from pi to 2 pi, and concave down, negative f double prime, from 0 to pi. On this next example, you're going to get to use the Desmos graphing calculator. So we're giving you the f prime of a function, e to the sine of x, over the interval from 0 to 3. See if you can use the calculator to figure out where the original function is concave down. All right, let's see how that went. So if I want to know where f is concave down, it would be helpful to know where f double prime is negative. So if I already have f prime, let me just take one more derivative on that. We have the derivative of e to the something. That's also going to be e to the something times the derivative of the something. So derivative of sine of x would be cosine of x. And at minimum, we'd like to know where this equals 0. It's not undefined anywhere, but at least 0. And then we can figure out where we're going to be negative. So go into Desmos. Let me put in my function here, e to the sine of x times cosine of x. And we have the interval from 0 to 3. So let me change my x-axis from, let's say, -1 to 4, just to get a good window. And if I click on my function and see where this thing is crossing the x-axis, it happens at pi over 2. So here's the picture I just looked at. We see that we have a critical value at pi over 2. And we see that after pi over 2, f double prime is less than 0, is negative, from pi over 2 to 3. So this is telling us that f is going to be concave down on that same interval. One last thing we're going to do with concavity is use it to make value predictions in certain situations. So let's say that f is a twice differentiable function increasing on the interval from 1 to 4, so we already know it's going up no matter what. If f of 1 is 2 and f of 2 is 4, we want to match each description of f with a possible value of f of 4. So basically, if f is a linear function based on these initial values, which of these outputs makes sense? If f is concave up, which of these makes sense? So pause the video and give this some thought. Now, for my part here, my strategy on these is I usually start by finding the linear output first, because that's the easiest. So just to demonstrate this, I'll do a little bit of a graph. That's also a good strategy. So I've got the point 1, 2, somewhere around here, and then 2, 4 is a little bit to the right and up. And then if I'm looking for a linear output, if I extend a line through these points, I'm asking basically what is the output when x equals 4. If I'm going over 1 and up 2, over 1, up 2, over 1, up 2, this is going to have to be up 4 from the last point here. So this would be an 8. And that would be option D. So the line's pretty easy to find. Now, if you already know what the line should be, you can actually find concave up and down pretty quickly. Concave up, if you draw a picture like so, you'll notice that a concave up increasing is going to be greater than the linear output. So which of these answer choices is greater than the linear answer? Well, 10. That's the only one bigger than 8. So choice C for that one. Concave down, same kind of idea. Let me draw a concave down curve. This looks like it's going to be under the linear, less than the linear. But there's two answer choices that are less than 8, 4 and 6. So the key with concave down is that we're still going to be changing. So we would pick option 6 here, option A, not option 4, because we want it to be changing from y equals 4, not just staying the same. So that's it for this one. Just one parting thought. Why do you think the line was happy with his trip to the dentist? Because he had no concavity. Ha ha. Till next time, Mr. Sutton signing off.